this is Saptarshi here, and I welcome you back on course on machine learning using Python. So we are going to look at a hands-on session today. The hands-on we are doing on Kaggle, our usual environment, and we are going to focus on k-Medoid algorithm today, which is a clustering algorithm. And basically the motivation is to improve k-means because k-means has certain particular disadvantages. If you want to know more details, you can look at our theory lecture on k-Medoids from our YouTube lecture. We are going to focus on 5 questions today. We are going to focus on how to fit k-Medoids. Then we look at how to calculate Shillute score for a cluster. What is Shillute score? Shillute score is a mechanism by which you can compare results of clustering. Okay, so if you have to compare one clustering result with another, Shillute score can give you a basis for the same. Okay, then we can see how this can be used to find optimal number of clusters. Then we look at purity, which is also a cluster validity or cluster quality measure with a subtle difference, which we'll discuss when we'll go to that particular question. And then we will go to question 5 where we look at how extreme observations affect k-Medoids compared to k-means. Okay. Now this k-Medoids is not directly available in sklearn. For that you need to install sklearn extra. So this is the way you can install sklearn extra. You can just run the cell and it can be installed. For paucity of time, I have already installed it. Okay. Now let's go to our few housekeeping. Let's import numpy, matplotlib, pandas, then k-means from sklearn.cluster and k-Medoids from sklearn underscore extra dot cluster. Let's run this quickly. Now let's go and fit our k-Medoid. So we are going to use the familiar iris dataset. Okay, so we are going to import datasets and then we are going to use the method load iris that will hold in a variable called as myiris. Myiris.data will get the independent variable and myiris.target will get the target variable. So let's run this quickly. It is run now, so you might be interested to look at x. So let's look at the shape of x. Okay, so if I do a x dot shape, okay, so it tells you that there are 150 rows and 4 columns. And if I want to look at y, it should have 150 rows and of course it has 1 column. Okay, and if I want to look at how y looks like, okay, so y has values like 0, 1 and 2. Why 0 and 1 and 2? Because iris has got 3 classes. So as you know, k-means, knn, k-Medoid are based on distance measure. These are quite affected by scale of the variables, original scale of the variables. So it is important that we bring all the features to a comparable scale, and that is the reason we are going to use standard scalar over here. Okay, and we are doing a standard scalar dot fit. Then we are doing a scalar dot transform, and this is imported from sklearn dot preprocessing. Next, we are running or initializing k-Medoid with number of clusters as 3 and with a random state value of 0. Okay, then we fit x scaled and finally we use this to assign the or find out the cluster labels corresponding to the different observations that are there. So once this is run, let's look at why k-Med. Okay. So why k-Med should actually have values of 0, 1 and 2. Okay. So let's look at some of the other things k-Medoid can have. So let's just look at what all parameters it has got. So you can just put a dot and then a tab, and it can give you some of the things that that are available. So you can go and look at any one of them. Let's look at this inertia. Okay, so let's look at what is the WCS value. So it comes to 131, though we don't have a reasonable basis to compare, but this is how you can access different components of this particular model. Okay, all right, now let's see how to use Shillute to evaluate cluster. Okay, so this needs some discussion about the Shillute coefficient. Okay, So let's just understand this, that Shillud coefficient is calculated for each of the observations, okay? And then it is averaged out. So if you have 100 observations on which you are doing clustering, for each one of them, you find Shillud coefficient. Now what is BI? BI actually tells you the difference with other clusters. So you remember that actually good clustering means that you have within cluster small distance and between cluster high distance. So A actually indicates within cluster distance and B actually indicates between cluster distance. Okay. And then you divide this by max of AI and BI. So let's understand this with an example. Okay. So here what we are doing is we have two clusters which is univariate. So you have only one variable. One cluster has got values 1, 3 and 5. Another has got values 7, 9 and 10. Okay. So first what we do is within the cluster I try to find the distance for each of the observations. So I find distance of 1 with 3 I get 2. For 1 with 5 I get 4. Similarly 3 with 5 I get 2. 3 with 1 I get 2. Okay. For 5 with 1 I get 4 and 5 with 3 I get 4. Okay. So A is nothing but average of this. So 2 plus 4 by 2. So I get a 3. Here I get a 2. Again here I get a 3. Next what I do is I find out the distance of this point with all the points from cluster 2. Okay. So here the example is done with two clusters, and generally for the second cluster the nearest cluster of cluster 1 is picked up. And also remember, definition of Shillud is dependent of another cluster, so you at least need two clusters in your data to calculate the Shillud. Okay, so from 1 the distance of the points 7 is 6, 9 is 8 and 10 is 9. So we calculate 6, 8 and 9 and we calculate the minimum of this, right? And then what we do is we use the formula that we have shown earlier. So we do a B minus A which comes to 3 and then max of AI and BI which is 6. So 3 by 6 is 0.50. Okay. And look at the last one, the value comes to minus 0.33. Why this happens? Because it's B is less than A, right? So that means the other points or the points from the other cluster are closer to it compared to its own points. Okay. So actually Shillud coefficient has a range of value from -1 to +1. Finally you take an average of these three. Then what you do is you repeat that for the other cluster in the same way, right? And if you average, you will see that maybe the second cluster has a better Shillud coefficient than the first cluster. So another good thing about your Shillud coefficient or Shillud score is that at an individual cluster level also it gives a quality of the cluster. So here what we are doing is from sklearn matrix we import Shillud samples and Shillud score, and let's run k-Medoids and look at what are the values of Shillud average. So the Shillud average comes to be 0.45. Okay, so which is not a very bad value, right? So it is as closer to 1 the better the clustering is. Okay. And also what we can do is we can actually for each of the clusters we can find out the Shillud score. Okay, so for that what we have done is we have used this function Shillud samples, okay, which takes these two parameters x scaled and y k-Med similar to Shillud score, and then I run for the number of clusters that are there and take the Shillud value for one cluster in each iteration of this loop, and then we report the average value. So if we run this, okay, so I get the average value of the different clusters. So if I look at, I know that my cluster 1 is the best cluster followed by cluster 2 and cluster 3. Okay. Now, can we use Shillud width to find number of clusters? Yes, on very similar manner like we were using within cluster sum of squares, we can just run this, okay, with different values, okay, with different values of the cluster, and then we can find the Shillud average, okay. All right. So if I do this now, my Shillud width is populated for different, different values of the clusters, okay. And if I plot this, you see that initially you have a silhouette width value and then you are going down. So you can kind of use the same same average value concept, same elbow value concept, and find the number of clusters. So with 3 clusters, there is a good silhouette width, and lower the silhouette width, worse the clustering is. Okay. So you can see that here also there is a tendency to have high silhouette widths with less number of clusters. Okay. All right. Uh, Now let's look at the third question, that how to, or the fourth question, how to compute purity. Okay. So this is also one of the important concepts. So let's understand with an example. So let's say purity. Okay, so let me tell you first the basic thing about purity. So purity is used when you have class levels available. Okay. All right. So you have class levels available, and then you are testing that whether your clustering is aligned with your class levels. Ideally, if you have such 2 classes, then there should be 2 cluster forming, where one cluster go to one of the classes, or one class goes to one of the cluster and the other class goes to the other cluster. So here, let's say originally you have 100 observations. Okay, you have 100 observations, and what you are trying to do is you have first plotted, looked at cluster 1. So cluster 1 has got 50 observations, out of which 30 are class 1 and 20 are class 2. So you are going to take the maximum of this and take a ratio of that with the total number of observations in the cluster. So it turns out to be 30 by 50, which is 0.6. Similarly, for cluster 2 also, it is 0.6. So overall, it is 0.6 into 50 by 100 plus 0.6 into 50 by 100. So you get a 0.6 overall. Okay. So here what is done is, now these clusters are becoming more homogeneous. So from 30-20, now you have 10-40. Okay, so now maximum is 40 and your purity is 0.8. So finally you are getting an overall purity of 0.8. Also, let's look at another example where intentionally what we have done is, so one of the cluster is very good. Okay, so all of them belongs to class 1, or most of them belongs to class 1. So this cluster has a very good purity. However, cluster 2 doesn't have such a good purity. Okay, so it is almost mixed bag between class 1 and class 2. That's why the purity is very less. And if you just multiply by number of observations and then take an average, it comes to be 0.68. So that's how purity is calculated, and that's what this formula also talks about. Okay. All right. So purity is not directly available. So for that, you need to run this method. So what we are going to use it, we are going to use the actual levels, because this is like a classification, and we are using the y-pred, which is our predicted value. Okay, so let's run this. Okay, so now our purity function is available. Now let's look at how extreme values affect k-Medoid compared to k-means. Okay, so let's run k-means once, and let's look at what is the purity score. Okay, so if we run k-means with our original configuration of 3 observation and initialization is random and all that, okay, we get a purity score of 0.8133. Okay, let's quickly visualize this with a scatter plot. So what we are doing is, different clusters we are plotting by different color. Okay, and we are also plotting the cluster center. Okay, so this is how the clusters look like. So there is some amount of overlap over here, and these are your centroids. Okay, now let's do the same thing with k-Medoid. Okay, so k-Medoid, let's run on the same data. Okay, same scale data, and let's calculate the purity. Okay, so yes, there is an improvement in purity, but by 2%. So we don't worry too much about it. Okay, so let's again plot this one and see how this looks like. So actually, you don't see that much of a difference. Still, they are quite overlapping. Okay, now what we are going to do is, we are going to add some extreme values. So what we are going to do is, we are going to add 3 observations with values like 10, 10, 10, 10, 15, 15, 15, 15, and 12, 12, 12, 12. Okay, So these are quite high values compared to the original values that are there in iris. Okay, so you already have x scaled values, but you can look at x. Okay, so if you look at x, you know, the values you will see are quite different from what we have given over here, right? So what we are doing is we are actually adding up these values, and we are also uh, appending three class levels corresponding to that, because we'll have to actually make m and y of same shape. Okay, so let me quickly see if we have already some value in m. Yeah, so we have already some value in m, and let's look at m dot shape. Okay, so you see the three observations are added over here. Let's also look at y dot shape. Yeah, so this part is not run, so let me run this part. Okay, so now if I run y dot shape, y is also 153 and our aim is also 153. Okay, all right, now let's do our standard scaling. So we do the scaling, and now we run on this data where we have added these three extreme observations, and we are calculating the purity score. So you can see that there is a significant drop from 0.81 to 0.67. Okay, so these observations are affecting the cluster quality a lot. Now let's run k-Medoid and see what happens. Oops. If you remember, with those observations, original 150 observations, the value was 0.84. Okay. However, when you run with these three observations, actually purity has not decreased, rather it has increased. Okay. So the cluster quality actually is getting better. Now let's look at how this looks like when we plot with k-Medoid. Okay, how the k-Medoid plot looks like. Okay, so if you look at the k-Medoid plot, see these 3 points has not really affected this cluster. This has identified part of this particular cluster. Okay, and the center is also not drawn towards it. As you know, Medoid is one of the original observations. So this is one of the most important pictures of today's class. Okay, that this original observation doesn't disrupt the clustering and or the cluster centers. Okay, so we can understand this better if instead of using yk-med, we use yk-means. Yes, so yk-means is the variable. So instead of yk-means, yk-med, let's just change it quickly to yk-means and see how this looks like. Yeah, so let me quickly copy this, and we can replace in all the 6 places. Okay, and basically we are not sure how this will affect the y-k-means result, okay, of these extreme observations. Okay, and here also, what was the name of the object? Let me quickly look at. The name of the object is k-means, so I will have to do k-means cluster center. Okay, so there are 3 cluster centers, so essentially I'll have to change k-Medoids to all the 3 places. Okay, all the 2 places, because we are looking at 2 variables. So if we run it now, okay, so there is some issue because we have used y-k-med over here. So let me just remove this and run again. Yeah, so now if you look at the cluster, just see what has happened, right? So these 3 points has formed a cluster on their own. Okay, so that's the biggest difference between k-Medoid and k-means. This is the most important question that we tried to answer over here. Okay, also now we can plot, we can look at the different accuracies that we have received. So we have included all the accuracies that we got so far for iris, and we have used a bar plot to find it out, and just look at the results. Okay, so this is k-means. Okay, and you see how it has been affected by adding up these outlier or extreme values. However, look at k-Medoid, there is almost no change, rather there is an improvement. Okay, so that is why k-Medoid is much more robust to extreme values. Okay, so thanks a lot for watching these videos, and you can give your question on the comment section and we'll try to go through all of them and answer. Thank you so much for watching.